Binding energy. The notation of binding energy is BE. Some book you can find EB. Okay? So, in general, the term binding energy is related to the nuclear fission reaction and also to the nuclear fusion reaction. Okay? Let's start with the fission reaction. In general, in the case of fission reaction, we have a heavy nucleus. The nucleons inside the nucleus are bounded together by the nuclear strong force. Okay? In order to break apart the components of this nucleus, we need to apply a certain quantity of energy. This energy required to break apart the nucleons or to break apart the nucleus into individual nucleons, it's called binding energy, BE. So in general, in the case of any nuclear reaction, we have the conservation of energy between before the collision, before the reaction, and after the reaction. Here, before the reaction, we have the energy of binding energy, the incident energy, plus the energy of the nucleus. The rest mass energy. For each quantity of mass, we have the equivalent quantity of energy. E equals to mc square. So the energy of the nucleus equals to m of the nucleus times c square. And the result of the reaction will be the individual nucleons. The total energy of the nucleons equals to m total of the individual nucleons times c square. The total mass of the nucleons equals to the mass of protons, Z, the number of protons, times mp, the mass of one proton, plus nmn, the number of neutrons, times the mass of one neutron. Okay? So in general, we have the total energy before the reaction equals to the total energy after the reaction. If we divide all the equation by c square, here we can eliminate c square, and here also. So finally, we get a small value, BE divided by c square. E equals to mc square. So m equals to the energy divided by c square. So this quantity is a quantity of mass. We can say it's called, or it's noticed by delta m. Delta m plus the mass of the nucleus equals to the total mass of the nucleons. We can say the mass of the nucleons equals to the mass of the nucleus plus a small quantity delta m. So the total mass of nucleons is bigger than the mass of the nucleus. Okay? Because you have delta m here. We can say delta m equals to the difference of masses between the mass of the nucleons minus the mass of the nucleus. Okay? Let's go to the nuclear fusion reaction. In the case of nuclear fusion, you have a light particles can be combined together to create a new nucleus. Okay, for example, I give a simple example here. We have two protons and two neutrons can be fused together by a nuclear reaction to get a new nucleus of helium, He42, with two protons and two neutrons. And after the reaction, we have a quantity of energy released from the system. So this energy also is the binding energy. Okay, it's the binding energy. If we do the conservation of energy between before and after the reaction, we do the same like before. We have the energy, total energy before, equals to the total mass times c square, equals to the energy of the nucleus, the created nucleus, which is equal to the mass times c square, plus this energy, which is binding energy. Here, let me write the equations. You know, we calculated before, we have the energy of the nucleons equal to the energy of the nucleus plus binding energy in the two cases, fission and fusion. Okay? We can calculate the value of the binding energy Be, which is equal to the energy of the nucleons minus the energy of the nucleus. Okay? We divide by c square, we get Be divided by c square equals to the mass of the nucleons minus the mass of the nucleus. Okay? This quantity of mass, or the difference of masses between the nucleons and the nucleus, is the mass defect. We can say delta M. Okay? Delta M equals to Be, binding energy, divided by c square. So from this equation, we can calculate delta M and we can calculate the binding energy Be. But in general, I give you the value of Z, for any element from the periodic table. You have the proton number, you have the mass of proton is given, the number of neutrons, the mass of neutrons are given, but we don't have the mass of the nucleus. In order to calculate M nucleus, we can say the total mass of the atom equals to the mass of the nucleus plus the cloud of particles, the masses of the electrons outside the nucleus. Okay, so we have the mass of the nucleus plus Zm electron. You know, in the case of a neutral atom, we have Z number of electrons. The number of the negative electrons equal to the number of the positive charge. Z proton equals to Z electron. So we can substitute the value of, ZMP plus NMN is the mass of the nucleons, the mass of nucleons. And we can substitute the value of M nucleus by M atom minus Z M electron. So we get finally delta M equals to the binding energy Be divided by c square equals to the mass of nucleons minus the mass of atom in general minus Zm electron. From this relation, we can calculate easily the value of delta M and the value of Be. I give you a simple example here. Calculate the mass defect of carbon 12, 6. You know here A equals to 12, Z equals to 6, and N equals to A minus Z equals to 6. I give you the mass of carbon nucleus, okay? It's not the atom, the nucleus. I give you directly its value. I ask you to calculate the mass defect of carbon. You know the mass defect in general equals to the mass of the nucleons. We can say ZMP plus N Mn minus the mass of the nucleus. We can say Mn. Okay? We have Z equals to 6. We have MP equals to 1.007276 U. We have N equals to 6. We have Mn equals to 1.208665 U minus Mn equals to 12.996 atomic mass unit. We can substitute all the values here. We get finally the mass defect equals to 0.098940 atomic mass unit. Okay? One of the most important experiment quantities is the binding energy per nucleon, BEN. In general, the definition of BEN equals to the binding energy total of the nucleus BE divided by the mass number A. You know, the binding energy equals to the energy of the nucleons minus the energy of the nucleus. Okay, divided by A. You know, in general, as definition, physically, the binding energy BEN per nucleon is the energy required to remove one individual nucleon from a nucleus. We talked about, you know, the nucleons inside the nucleus are bounded together by the nuclear strong force, by the strong nuclear force. In order to extract or remove one nucleon from the nucleus, we need some quantity of energy. This energy is the binding energy per nucleon. It's very important to calculate its value. Why? Because by calculation of binding energy per nucleon, we can classify all the nuclei, which one is stable, which one is less stable, which one is unstable. Okay, you know, we have radioactive, I mean unstable nuclei, and we have a non-radioactive nuclei, I mean stable. Be careful. When I say radioactive nuclei or radioactive element, I mean it's unstable, okay? Because it has the ability to decay with the time, or it's able to have some spontaneous fission or any kind of reaction, okay? And when we talk about a stable nuclei, I mean it's non-radioactive element, okay? For this reason, we have some. Here I present all or some elements here with the mass number A in terms of the binding energy per nucleon. If you look well here, for a light nuclei, for example, we have the deuterium H12. you know, in the deuterium nucleus, we have one proton and one neutron. In order to remove one nucleon, we need only 1 mega electron volt. It's relatively small, okay? And each time we increase the number of A, the mass number A, the binding energy increases. We arrive to A equals to 60. At this point, we have the most stable nuclei. It's the zone where we have all the most stable nuclei. And the most stable nucleus is the nucleus of iron 56, Fe. If we increase the mass number here, the binding energy decreases. Why? Because you know the heavier nuclei are less stable, okay? And the elements here have less, we can say, have a binding energy less. In this case, it's easy to have some splitting of the nucleus for the heavier nuclei, and also they have less binding energy per nucleon, okay? For heavier nuclei, I mean for the nuclei here, the energy is released when they break up. What I mean, when we have fission. Because they are very heavy, in order to have energy, or we have energy after the fission reaction, okay? Because they are heavy and the binding energy per nucleon is small. But in the case of lighter nuclei, here we have energy, or the energy is released only when they fuse together, okay? Because they are light. In this case, after the fusion reaction, these particles will fuse together and we get the nuclear fusion energy. In general, we have a competition, or we can classify all the elements by 3 parts. First of all, we have the lighter nuclei. They do fusion and they decay, okay, to a stable nuclei from this zone, okay? Yani finally, the lighter nuclei will be transformed to a stable nuclei near to the zone of A equals to 60. The second zone is the heavier nuclei, where all the elements must have some fission, maybe spontaneous fission. After this reaction, these elements will be transformed to a stable element, to one of these elements in this region. If you want to do some nuclear fission reaction, you have to choose a heavy element. For example, in general, you know, in the case of nuclear fission, you take the uranium-235 because the nucleus is relatively large. You have a large number of protons and neutrons. So this nucleus is able to do some spontaneous reaction, spontaneous fission, to split or to break apart the nucleons. And we can get the released energy, okay? And also, in the case of the third zone, we have the stable nuclei zone, where You know, most of the stars in the galaxy, after a series of decays, they become iron, Fe56, because after a certain time, the unstable nuclei will decay to a stable nuclei. Okay? Here, I give you a simple example. I want to find the binding energy per nucleon of helium-4, He4 2. You know, in general, the binding energy per nucleon, BEN, equals to the binding energy total of the nucleus divided by the mass number A. To calculate the binding energy, BE, which is equal to, equals to the mass defect delta M times C square. Okay? And A equals to 4. Delta M is a mass defect. I give you mass defect equals to 0.030377 U. What about C square? As we have the unit of the mass in atomic mass unit U, you have to put the value of C square equals to 931.5 MeV divided by U. Okay, you can eliminate U and U. We get finally the total binding energy of the nucleus equals to 28.3 MeV. So it's the total energy required to break apart the nucleus to the individual nucleons. Okay. What about this is the value of BE. To calculate BEN, we divide BE divided by 4. The value will be 7.07. It's the energy needed to remove one nucleon from the nucleus. Okay?